like that. So the main thing is just you should understand what we are going to learn, why we are going to learn, and what is that we are supposed to do after learning this course, computer architecture and organization. That was my agenda of last uh, first lecture. That is introduction. So there is no need to go deep in that. There were some students requesting to go slow, but just like overall thing, you just need to know what are this subject is constituting, what is essential, why it is necessary for a electronics engineer. So that's it. Right. So yesterday we discussed basics of digital electronics overview. So main important thing in that this is big difference between sequential and combinational. So I hope you got those concepts. This is combination logic. So what is the specialty of combination logic? Combination logic doesn't have any memory. That's the main thing. Whatever input, you have n number of inputs, and you'll get outputs instantaneously based on the logical relationship between inputs, or what is the circuit or logic we have designed. Right. So a lot of gates. So basically, combination logic consists a lot of gates, and gate, or gate, NAND gate, NOT gate, all those things, all those gates. Gates work instantaneously. Whatever the input is given to them, they act on this input, right? So there may be some other gates also. Mm, yeah, maybe NAND gate, NOT gate, some lot of, and maybe the blocks combining this, maybe mux and all those things. So all these are also multiplexers. Sorry, combination logic. So the combination logics works instantaneously. What are the input? The input flows to the logic gates, and they after a propagation delay. This one of the important concept you should know. There's always a propagation delay. T propagation. Each of these gates have a T propagation. NOR gate, AND gate has different, maybe different, and NAND gate have a different T propagation. So after a propagation delay, we'll get the output. So total propagation delay I call T, capital T and P. So my input is given here 10011 something, and after the propagation delay of capital T underscore P, I'll get my output. Surely I'll get my output, and this output is only a function of your input. Output is only a function of your input and doesn't depend on any of the previous input or output. So it is instantaneous. This all things are action instantaneous. Only thing is there is a propagation delay. Each of these gates has some propagation delay, right? That's we'll discuss later. What is the effect of this propagation delay? Yeah, there is some negative effects of this propagation delay, which you might not have learned, but you know there are different paths. You can say that different paths. Um, one path is this, and that path may be this. So both these paths has different number of gates in their path. So there will be different propagation delay for different signals within your combination circuits. That is the only complications we face in combination circuits, right? Difference in propagation delay. AND gate has a different propagation delay. T AND gate, propagation delay AND gate, not NOR gate might have different, and NOT gate might have different, and all those. So all these gates are different propagation delay can cause different path delays to your signal, and they may cause some glitches in the output. What is glitches? Something, some extra, some slight pulses which we don't want. Maybe for less, maybe picosecond or femtosecond. It may be less or it may be huge. Sometimes maybe something like this. So these things we don't want, but that's the only challenge in designing combination circuits. There may be some glitches. Okay. So now the combination circuit doesn't have any memory. Now let's consider the sequential circuits. Now sequential circuits are circuits which themselves have a lot of combination circuits, and they'll have memory. They'll always have a memory also. Memory elements. So what are the memory elements? Memory elements are maybe flip-flops, maybe two inverter connected back to back. These are all memory elements. So memory elements may be taken from the feedback. Maybe some previous output is going to input your memory element, and this is stored in the memory. And this also can come as your input also. So the only thing difference in sequential logic is combination logic combined with the memory elements. This is combination only. because any digital circuit will have a lot of gates, so that constitute the combination logic, and they have some memory also, previous memory. So this may be some storage like 101, something will be stored in memory, and this is going to affect your present output, right? Your present output is a function of present input as well as previous input or previous output. That is memory. So this is the sequential logic which I was shown. So sequential logic is nothing but a combination logic and having some memory elements, some registers, or maybe some inverters back to back. So I'll explain how the memory is designed using inverters. So this is about sequential logic. So what about inverter example? So suppose I have an inverter. What is inverter? Not gate. Not gate. So not gate itself has a combination logic, right? Why? Because whatever pulse I'll give, based on this pulse, immediately I'll get output. This is one, this is zero, this is one, this is zero. So I'll my output is instantaneously. I'm excluding the propagation delay here. Although all the gates will have a propagation delay, but we assume that there is no propagation delay. Ideally, this is an ideal NOT gate. So your output is 1, 0, 1. So this is a combination logic. Now, how can I make this sequential? The one solution for making combination logic sequential is give a feedback, feedback, feedback. If you give a feedback, your output is connected to your input. Whenever you have feedback, your output is connected to input. So even if your real or original input is not connected or not given to the circuit, your feedback will always feed your input, right? That's the logic of feedback. So whenever you have feedback, there is a high chance that you have memory. So feedback gives memory, and this memory is what makes the sequential logic, right? So this is the sequential logic secret. We'll have a feedback. We'll have feedback. We have path from the output to the input. Now let's see. I cannot give feedback in this circuit because this is not logical. Input is 1, output is 0, and this 0 I cannot feed back to the input. Why? Because there's a shorting. Input is high, output is low. Now I cannot connect this 0 to 1 because high voltage is plus 5 volt, 0 means ground, 0 means ground. So 5 and ground I cannot short. So what happens? Here it will be shorting of the high voltage VCC and ground take place, and a lot of power dissipation. A lot of current is flowing through this. Not maybe there are short circuit. High current means high temperature, and high temperature causes fire. So this is a short circuit example, but logical there is no logical reason of shorting the input and output in this case. Now let's take another case. Now let's take another case. Now I have a NOT gate. I'm keeping two NOT gates. So that logical relationship is um, maintained between input and output. So this is input. Input is 1. Intermediate output is 0. Again, output is 1. Right? If input is 0, intermediate output is 1. And again, the second NOT gate will be giving 0. Now we can see the input and output are having same logical value, 1 and 1. And here also 0 and 0. Now I can think of a feedback. Now in this case, I can have feedback. I'll connect. This is the output, but still I'll take one part of connection to output and give it to the input. Right. So this is kind of feedback. Now this is the original input was there. Some input was there originally. Now even if I make it off, even if I don't give the original input, my feedback will be maintaining or strengthening the input of my NOT gate number 1. Right. So here I can see that even if I don't give an input is taken off, the feedback is always feeding my input of the first gate. Okay. So this is kind of feedback. Now this you can say I don't need any input. Even if I take away the input, my 0 is always stored. So this is kind of a memory. Now I'm giving memory element. Now I designed a memory element. Now 0, which is a stored element. Here I can say I'm storing 0. Or maybe you can say I'm storing a 1 in between. If you consider in between, I'm storing a 1. And actually I can store 0. But both are not dependent. If it is 1, output is 0. Output is 0, input is 1 on reverse. So only 1 bit I'm storing here, not 2 bit. Right? because one bit decides all other bits. So I'm storing only one bit here. So this is the circuit of, you can say, SRAM. SRAM circuit, two inverters connected back to back. This is a memory element. Okay. So what happens here? I have feedback. That's the main thing. Whenever I have feedback, there's you have memory. So this is the concept is same in the flip flop or latches also, right? So this is kind of feedback. But only thing is we have propagation delay, T propagation of the NOT gate is this, and T propagation of this NOT gate is TP. So total propagation delay is 2 into TP. So whenever input changes, the output is reflected in the change in reflected in the output after 2 into TP propagation delay. Okay. So we have feedback here, and when feedback, we have a memory. So this is the main takeaway from this example. So now this is the circuit of the SRAM cell, which we will discuss later. So if you need how many one inverter, you already know how many gates, MOS gates you need. So this is one inverter with the top PMOS and bottom NMOS. So this is VDD. You can say plus 5 or VDD, and this is again connected to another inverter. It's also plus 5 volts. Now this is your output, and this is your input. This is your input. This is your output. So you can say one memory cell, simple kind of memory cell. I need only 4 transistors, 2 PMOS and 2 NMOS. Okay, this kind of a SRAM cell. Now feedback, you need a feedback. So this is connected to the input of, right? And we need one switching to the input and one switch to the output, so that I can take output wherever I want, whenever I want. I can change the input whenever I need. Right. So we need 4 minimum number of transistors in a storage is 4. So but we need two more transistor for input and output. So I need one more to fix one more transistor in the input, one more transistor in the output. So that will be a simple MOS and MOS. So this is while writing W. So that if I need to write, I need to make this one. And reading, this is for reading. Whatever stored, I need R, right? So how to write something? I'll make some bit high and I'll make W equal to 1. So this high is charges, or this high voltage is going to the input of the inverter, becomes high, from 0 becomes 5. Now 1 is charged. So this 1 bit is stored in the SRAM cell. Right now, reading, I need to read R equal to 1. I need to put R equal to 1. So this charge is voltage transferred output. And an output, I need a lot of sense amplifier sensing whether the voltage is high or low. So I sense what is the bit is stored, and I'm taking this into output. So each of these bits are stored like this in a SRAM cell. So you know that is why SRAM cell is having 6 transistors, 6T. You got 6T cell, called 6T cell. So you need 6 transistors. So it is a bit like, each bit we need 6 transistor means, the size of the SRAM is very large. And definitely the memory size is large, will be costly. And if you want high speed memory, we need to use SRAM, this kind of things, because it is purely logic, few gates logic, sequential combination of sequential logic, few gates are required. So, but in DRAM, dynamic RAM, we need only 2 transistor or 1 transistor. Okay, so the size is much lesser in DRAM. So we have, less cost also. We can have more packing density in DRAM. So we use it for primary memory incubators. And this kind of SRAM is used for register memory, registers, designing registers. Flip flops are another option. So yeah. Okay, now we'll go to the. So this is about so let me. I hope I'm audible.
Yes, sir.
There is an echo. Okay, fine. So
So then we have flip-flops also. We discuss synchronous and asynchronous. So, so two kinds of circuits, synchronous and asynchronous. Synchronous circuits are those where the whole chip or the whole circuit or the whole module is synchronized by the clock. Clock is telling me when to start the input, when to stop the input, when to start a process, etc. So all those are synchronized. Synchronized by a common signal which we call clock. Asynchronous circuits are can also be sequential. There's nothing between sequential and combination can also be sequential, but there will not be a synchronous signal, right? We can say, have you heard about there is two modules A and B try to communicate with each other. So the A starts a signal, let me send start, and B start, yes, you can start. Then A starts sending signals to B. So this is a handshaking signal, synchronous signals. We don't have a clock, right? We are on a global clock which controls all the input and output. So we have a lot of handshaking signals. Acknowledge, we know modem. If you studied modem, you know there's a request. Shall I sending request, acknowledge, sending data, acknowledge again, acknowledge from the receiver that I receive. So that is called handshaking signals. So if we don't have synchronous clock or something, we need a lot of asynchronous signals like handshaking signals. Although these asynchronous circuits are not a part of uh, your digital or your computer architecture, because mostly we use synchronous circuits in all these computers. But there are some cases we use asynchronous because sometimes synchronous also can be slow. So why should I wait for a clock when I can do complete the process faster than the clock? So clock is global. So we have to design clock or man should put clock should be able to all the processes in your chip, all the processes in your module should be completed in that time. So our clock cannot be optimized, right? Because it has to wait for all the different logical execution in your chip or in your module. So sometimes we don't need to wait for clock. Let us start process as soon as it is done. Based on the propagation delay, let me do my process. So that is kind of circuits or asynchronous circuits. I don't wait for clock. Waiting for clock is slow, right? Let me do my own processing and using handshake signals. When I'm finished, I'll say, okay, I'm finished. Let me start the next process. Okay, like that, like that. So although it can be a bit complicated, but it is in some circuits can be very high, faster than the clock circuits. So there was something which we you already seen that this is also feedback. You can see the feedback here also, like in the so the feedback is here. I don't know why I'm not able to draw. I don't know, I'm not able to draw. Fine. So here also you can say feedback from the Q bar. Again, yeah, this is actually a NAND latch, and we are again connecting a clock so that the latch can be clock latch, right? So flip flops, as you already know, flip flops are edge triggered, or can say works or activates on the positive or negative transitions, right? So they are flip flop. Even though you connect a clock to a latch, it becomes clock latch because still it is working on level, right? It is working on level, not on the edge triggering high to low, positive edge or negative edge, right? Likewise, we can have a latch using NOR gates also. So you can see the pulse is only pulse, positive pulse or negative pulse. So it's level, positive level, it will be activated based on input S and R. My output will be changing, right? If S and R are 0, the positive pulse, there's no change in the output. And when S is 0, Q bar is 1. That means it is reset. S is 1, it is set. Q is 1, Q bar is 0. And 1 is prohibited because it is a raised on condition, or I cannot predict what is my output in this situation. So we should not use this 1 because I cannot predict what is the output in that situation. So in any design, if we don't know, if engineer, the designer don't know what is my output, it should not be used because unpredictable things should not be employed because it is it causes problems which we cannot expect, which we don't expect. So D flip flop, So D flip-flop. So if anyone has any queries or doubts, you can ask in between. So D flip-flop, we already know D flip-flop is called a transparent. Whatever D, it goes to the Q. So if D is 0, Q is 0. If D is 1, Q is 1. Okay, so we can say this is a flip flop. So flip flop is always triggered, edge triggered or level triggered. Here we can see it's uh, triggering from the low to high. That is negative to positive edge. So positive going edge of the clock, my flip flop is triggered. So D is 0. So Q is also 0. Only when the positive edge of the clock. D is 1. Q is also 1. Only in the rising edge of the clock. So it is, you can see the clock symbol here, an arrow. I don't know why I'm not able to write anything. Okay, enable editing. Okay, okay. So right now I'll make it. So fine. So you can see here there's an example of the waveform. So when the D, you can see D is high. D is not only D should be high. Your positive edge, you can see positive edges coming here. So at that point was a D. D is high. D is 1 here. So my output Q goes from 0 to 1. You can see Q is 1 here. Right now, the only next point to consider is the next positive edge of the clock. Now, at this point, your Q D is 0. So D is 0. So Q becomes 0. That means it comes from the high 1 to 0, comes to down. So this is the point my value is changing. Why? Because it is positive pulse. Positive pulse is deciding D should go to Q. Again, next time to consider is the positive pulse here. Here again, there's no change. D is 0 here. So output remains in the 0 state. Next point is here. The positive, what the D? D is 1. So again, my output goes from 0 to 1. Again, next point to consider is here. Although some D is changing here, but it doesn't affecting your output because it's only acting on the positive edge of the clock. Again, this 1, it remains in the high position. So the fluctuation in D is not affecting my Q because of the clock. So even some there is noise, some noise in between, I don't care because only point is my clock. As the clock transition from 0 to positive or negative to positive, I'm just checking my D. All other cases, it doesn't matter. Now next is this point, my D is 0, so Q becomes 0. Again this clock, Q is D is 0, so Q again remains 0, right? So you can see this is Q equal to 1, D equal to 1. All these places on the transitions only, the positive, negative to positive or positive pulse transition. I'm just checking the value of D and giving to Q. So this is called transparent flip flop. Whatever D is going to Q, so it's called transparent, right? Transparent flip flop. But only condition is only at the positive edge of the clock. If there is no clock, it will be a latch. So we can say it is a transparent latch. Whatever D is going to Q. But in latch, you're acting on the level. Level. I think this concept should be very clear. Level, clear. All this point of the clock or your uh, enable signal, your latch is activated. So this is level. But right now it is edge, positive edge or negative edge. Now this is a JK flip flop. So here also you can see it is activated on the positive, negative to positive edge of the clock, rising edge of the clock. So 0 0 there is no change, and 0 1, you know, K is 1, so Q is 0, Q bar equal to 1, and J equal to 1, set it is set, Q equal to 1, 1 1 it is toggling. So we are overcoming the prohibited condition or forbidden condition and just toggles in the prohibited condition. Now this is based on the clock pulse. I'm checking the value of J and K, and my output Q is changing based on the clock pulse and J and K values. Right, this is explanatory. You can see here the clock pulse is here. J is 0, Q is 0, J is 0, K is 0. So output is no change. And similar case here also. There is J is 0, K is 0. There is no change. Now when both are 1, we can say J is 1, K is 1 and the positive cycle. So the toggle Q is changing from 1 to 0. Again one more toggling here, 1 1 and the positive pulse. Again 0 to 1, it is going to 0 to 1. Likewise. And set is when J equal to 1 and K equal to 0. This is set. So Q is 0 to change to Q 0 to 1. It becomes 1. Clear? When J equal to 0, K equal to 1. Clear. And positive pulse of the clock. So clear is happening. Now, as for clarity, you should know what are the positive edges and what are negative edges. So in latch always acts on the level. This is the area where latch is triggering. So we can say there's a time, or a lot of period or duration where latch may be triggered. So it may trigger 1 or 2 or 3 or more time. We don't know how much times the latch triggers because so much of duration is there on level. So where the latch is triggering. So this is level triggered. But flip flops always trigger on the edge. This is positive edge. This is a positive edge. And this is a negative edge. Okay, so you can see the change in the clock, how we draw the clock. Positive edge, we draw the clock like this, a triangle. But in negative transition, we have bubble, negation. So this is a indication of positive and negative clocks or transitions, positive negative edge triggers. So this is, we already discussed, the clock is high, D is going to Q. Clock is high, the rising clock, D is going to Q, transparent edge. Negative, clock is low, the same thing happens. D is going to Q, same thing happens. JK also same thing. The clock is high. All the triggering happens when the clock is high or high pulse rising edge of the clock, and you can see the symbol of the clock is a bubble and a same thing. Okay, now this is another important thing: setup time and hold time. So we have whenever we design any circuit, ideally we think that input is high, output is coming instantaneously, but there is always a propagation delay because all your logic modules or circuits, all your circuits will be consisting a lot of gates, or these gates will have transistors inside them. So these transistors, as you know, will have some capacitance. Transistor always has some area, base area, collector emitter area, width, base width, collector width, emitter width. So all these have area. So whenever there is an area in any electronic or electrical part, there will be capacitance because capacitance is equal to epsilon 0 A divided by D. So there is an area, there is a distance between these plates. So there is always a chance of capacitance. We have some metals connecting semiconductors and your different collector emitter junction or PN junction, P-type junction, and the diode we have a capacitance. So all this capacitance effect will come across to cause a delay, RC delay, right? So we'll always have RC delay in almost all the circuits, electronics, electrical, whatever. So this delay, this causes a delay. So what happens because of this delay, your input applied to a module or a unit or a gate even will not be instantaneously passing. The voltage or the charge will not be instantaneously passed to inside the circuit. So we need some time before the clock, because clock is what? Clock activation, positive rising edge of the clock or negative edge of the clock, our process has to start. So before starting the process, all my internal capacitance, all the time delay or non-linearities within your modules or gates has to be addressed. So the minimum time before the clock, my input, the minimum time before the clock comes, my input has to be ready. Okay, that means you're in a train, you're waiting for a train, the train is exactly coming at 10 o'clock. So if I tell you have to be there at least 5 minutes before the arrival of the train, therefore your setup time is 5 minutes. Okay, so the clock is coming at this point, so your processing time your time of triggering, that means the positive rising edge of the clock is this time. So before this rising edge of time, how much before I should be ready, my input should be ready, so that for proper processing, right? So before the clock edge comes, my input should be ready before that. So how much time before my input should be ready, that is called setup time. The input would be set up some time t before the clock edge arrives, so that is called setup time. So why I explained why the setup time is important, because all the circuits and gates will have some transistors, some internal circuitry, some PN junction, whatever, and all this has some capacitance. So this capacitance has some delay. So input applied may not directly go instantaneously go to the output. So it needs some time to charge this capacitance to flow. The charge flow has to happen. There will be delay. So in order to address these things, your the designer or the manufacturer of the IC or a gate or a module will specify your input has to be ready, or input has to come to the gate before the clock is edge is arriving. That is called the setup time, right? So reason for setup time is beyond the scope of our discussion, and to calculate setup time, to how to find what is setup time, this is not in this course. This is maybe uh, you may learn this in advanced digital design course, right? So but you should know any modular circuit or a gate will have some setup time. So before the set, according to setup time, or my input should be ready at least, right? If you're not able to reach the station 5 minutes before the train, you'll miss the train. Why? Maybe there's some checking going on. There's some kind of police checking. There's a queue, something, whatever. So your input should be ready by this time before the setup time. Maybe all this are fine. And another is hold time. Hold time is also important, because your output or your the input has to, right, the input has to remain, has to be maintained in the input of the module or a gate or a logic, has to be maintained even after clock has passed, right? So that is called hold time. For example, you have started traveling, but your relatives or your friends has to remain in the platform even after your train has passed, so maybe 10 minutes. Even after your train has passed, maybe they have to remain there for maybe 2 minutes, 3 minutes, whatever. So that is called hold time, right? Hold time is also important. So because of the same cases, charge carrying and discharging of whatever, it's both most of a device thing. In order to calculate setup and hold time, you need to understand the capacitance of the transistors, gates, and all those. So this at least you have to understand what is setup time, what is hold time. Before the clock, my input has to be ready. So what is minimum time? Setup time. After the clock has gone also, and I need to keep my input, right? So that is hold time, TH. Now, in the flip flops, you should know there are some asynchronous inputs. That means they're not controlled by clock. They can override the clock. They're like the VIPs or the people who doesn't don't need to care about the traffic signals, because when minister is going, he will be going in, or ambulance. You can say ambulance is a better example. They don't care about the traffic signals. They can even jump over the traffic. So these are the asynchronous inputs in a synchronized circuit. Our flip-flop is a synchronous circuit, but these asynchronous circuits can override the clock. So these are preset and clear. Suppose you're using a flip-flop and you don't know what is your Q value. You're given a chip, so you know that is a flip-flop. So whenever you power on the flip-flop, you know there is a value of Q and Q bar. Q can be 1 or Q can be 0, and Q bar vice versa. So you don't know what is right now, what is my value of Q. It can be 1, it can be 0. There's a probability that it can be 1, 50% probability can be 0. So you don't need to worry. So you don't need to take chance whatever might be input. So you have to set it. You can set it. So there are two signals in your chip or in your module. There's a preset and clear. Preset means we are sure we want the Q to be 1. We can make the preset 0. This is very important. This is mostly in most of the practical examples, you can see preset is active low. Okay, active low. Active low means if it is 0, if it is given a low signal, low voltage, or um, yeah, low voltage, it is activated. That signal or the functionality is activated. You can see in the table, when preset is 1, clear is 1, there is no change. Clock is high, D is 0, Q is 0, transparent, right? And again, Preset is 1, clear is 1. Clock is activated, rising edge of the clock, it's transparent. Q, D is going to Q. Now, when I put preset 0, no preset, I'm setting prior at the prior time. So setting my, irrespective of the clock, rising edge or lower edge or lower high, my D is irrespective. D also it is not controlling this time. Output is directly changed to 1 setting. Q is directly changed to 1 setting. So preset is overriding your D and clock also. It doesn't matter where D, what are it clock. So preset is 0, output Q is equal to 1 and Q bar equal to 0, vice versa. Now, when preset is high, say clear. Now clear is low, active low. This is also an active low signal, clear. Irrespective of clock and data or D, our D Q is going to be 0, cleared. Your output is going to be cleared and Q bar equal to 1, vice versa. And both Q preset and clear are 0. Your Q and Q bar, Q will be 1 for preset and Q should be 0 for clear. So should we have illegal operation? So you should not work in this condition. So we should judicially give the input to this flip flop, either preset for setting, clear for resetting or giving some 0. So that is why you can see there is an active bubble. There's a bubble active low indication. Preset is active low, clear is also active low. This is usually. It doesn't mean that every time it should be like this. So you have to see the manufacturer data sheet to know whether it is active low or active high. So this is D flip flop preset and clear timing. So you can see here also. Yeah, when clock is rising, here preset and clear are high, so it doesn't matter. So D is whatever D is high, output is high. Next case, we can see rising edge of clock is happening here. Again, clear is high, preset is high. So D, what is D? D is 0. So output Q is coming back to 0. Okay, now let's see next edge of the clock is coming here. So let's see what is, but you can see the preset has become, yeah, you can see preset has become here before only. Here also the preset has become low. So it's active low. So preset means so Q, even if Q was 0, because of preset becoming low, active low, this Q is becoming high till this point too, and it is maintained. Right? Once preset is low, Q becomes high because active low, so Q becomes high from that point. Right? So it is maintained till it is triggered by some other clock pulses or something. So it is maintained. Even the clock is here, it is high, and D is 0. Still, it doesn't have effect because preset is low. This is have high priority. Preset have more priority than D and clock. Okay, so it becomes maintains or it maintains the high voltage or high value of Q is maintained. Now this clock is also done. Now the next clock is coming here. Now we can see the preset and clear are both high. So it is not activate, not having an effect on the Q. Now we can see value of D. D is 0. Okay. Now the output also comes back to value of D from high to low based on the value of D. Okay. Now let's see. Still we can see preset and clear is again high. So it doesn't matter. The next clock is coming here. So D is becoming high here. Okay. So my output is also becoming high from 0 to 1. It is rising. Now you can see after some time your clear is becoming low. When clear is becoming low, Q should be low. So Q should be becoming from high to low at this point. And this is maintained. The memory, because of its flip-flop, it is maintained. Memory is always maintained. Now you can see clear becomes high again. Preset is also high. Now it depends on the clock. Clock edge is high. And based on D is high. Now it becomes 0 to 1. Okay, it is maintained. It is maintained till next clock edge comes. Clock edge is 0 to high, rising. D is 0. So Q becomes 1 to 0. I hope this is audible. Right?
Yes, sir.
Okay, so this is a transparent latch. So in this we have a, I hope it is visible, right? Okay, fine, got it. Okay, so this is we have enable signal. Instead of clock we have enable signal. So when enable is 0, it doesn't matter what is the input, the old outputs are maintained. When enable is 1 only, my input is, or my clock or my gate or my module is activated. When enable is high, then D is going to Q. D is going to Q. So this is also transparent D latch. Doesn't have effect on the clock. So this is D latch. So this is example of D latch. We can see whenever enable is high, this window only, my D is going to Q. This window where my enable is high. In other areas you can see enable is not high. You can see Q is maintained. The memory is maintained from the previous data. You can see enable is 0. So whatever the previous Q, it is maintained here. There's no change. Okay. So whenever my enable is high, that time it is transparent. Enable is 0, memory gives whatever value of Q, latch the value of Q. Now this is basically the difference between latch and flip flop. Flip flop is having always a clock, and it is edge triggered, maybe positive rising edge or falling edge, positive to negative edge or negative to positive edge of the clock. And latch is always level triggered because level sensitive, and always edge sensitive. Now there are a lot of chips. Latches source chips is available. Flip flops chips are also available. So edge trigger D flip flop circuit. So now how this is happening? How we are able to uh, design a circuit which is edge triggered? Well, logically it seems how it's possible. We don't know. So the main thing is we have two circuits. Instead of one flip flop, D flip flop, we need two master flip flop and a slave flip flop. Now the main challenge of level triggering is you may be triggering multiple times. For example, level is high. This can be used for triggering multiple times, right? Because of the propagation delay of the gates within your flip flops or latches or circuit is limited. Because of the propagation delay TP, there can be 10 TPs within one level. So this can be triggering multiple times. So I don't want multiple triggering. So I use a edge triggered. So how to edge trigger? The input and output connection should not be maintained. That means my input should not be immediately instantaneously allowed to pass to the output. So that means we break the circuit into two. The input part circuit, or first part we call master. In second part of the circuit, this you can say output part of the circuit, it's called slave. So you can say master is active, slave is inactive because of this clock. You can see the clock because of this clock, right? This clock makes this. If master is active, clock is 1 is active. The slave is inactive because here clock is 0. So what is the advantage? I don't have a direct connection between the input and output. So there is no multiple triggering. I don't expect that as I change the input, my output is immediately changing. No, because output is not active. Slave is not active. At the same time, when my output is changing, whatever change in the input is not affecting my output. Why? Because output is changing, slave is active, master is inactive. Right? The clock is high, the master is active, slave is inactive. Clock is low, slave is active because the clock is 1 at this time. So whatever the input I'm changing in the clock master is not affecting the output, not affecting the slave at all, because the master itself is inactive at that time. So the main idea you should remember is I'm just disintegrating or dividing the circuit into two parts, the input part, the output part, and simultaneously both input and output are not active. That means my immediate changes in input is not going to the output. So when master is active, slave is inactive, and vice versa. So adding a clock pin to a latch does not make a flip flop. That is very important, and it makes a gated latch, right? So, but if you divide the circuit into master and slave, and master part activating on the positive clock and or positive level, and slave part activating negative level, will make it a latch. Sorry, flip flop. Okay, so you can read this. So the inverter connected between two clocks input ensures that the two sections will be enabled during opposite half cycles of the clock, right? So both are not active at the same time. When clock input is at logic 0, any changes in input signals cannot affect the state of outputs, right? That is the main thing. There is no direct connection between the input and output instantaneously. So we have a clock in between. So input signal master clock equal to 1 don't get reflected at the slave. Yeah, when clock is 1, master is active, it is not reflected at the slave. When clock is 0, the slave is active and the master input, whatever changes input is not reflected in the input to the slave. But the current state of the input lasts to the reached. So when master is inactive, whatever the output Q and Q bar is always input to the slave, because whatever input in the master is not affecting your Q and Q bar of the master. So the slave input is fixed because master is inactive. Master is not taking any input at that point. Okay, therefore output can only change when the clock signal falls from 1 to 0, while slave is active and the master output is fixed. So slave can take its own time and change. So the whole thing happens when the clock becomes plus to minus. This is the circuit of negative edge triggered D flip flop. Okay, so if any Q questions are there, I can take.